The first task at hand is to see if the center of gravity can be measured accurately enough by using unity. However, first the sign conventions and reference points should be discussed. Firstly, the reference is from the leading edge of the mean aerodynamic chord, meaning the coordinate 0, 0, 0 sits on the leading edge of the mean aerodynamic chord. This can be shown here. For this model, the z-axis is the longitudinal axis. A positive value of z will move the CG aft of the leading edge and a negative will move it forward. This shows a positive z coordinate, moving it backwards from the leading edge, and this shows a negative, moving it forward from the leading edge. To verify if the CG inputted and the CG found by using wheel reaction measurements were accurate, the real and the estimated values of CG were found. This was done by using the scales on the model in Unity and measuring the reaction on each scale for a range of different CG positions. These are the scales used in Unity. The estimated CG was found by using the forces on each gear and calculating the moment due to them. After this, the actual CG was plotted against the estimated CG on a graph, which is shown here. The graph ideally should have a gradient of 1, however this is not the case. This is most likely due to the scales on Unity only being to two significant figures, however this does show that the estimated CG is very close to the actual CG. Note that there are no values for the estimated CG when the actual CG is 0.16 and minus 0.35. This can be shown in Unity. When the CG is set at minus 0.35, the aircraft tips nose down as seen here. When the CG is at 0.16, the albatross flips the other way due to the nose up pitching moment. This can be shown here. Ideally, when the wheels are on the ground, the CG should be between minus 0.34 and 0.15 meters from the leading edge of the mean aerodynamic chord. However, to be safe, a range of minus 0.31 and 0.12 should be taken. For the static thrust test, different throttle settings or RPMs were used in Unity, and the thrust from each RPM was recorded using the following configuration, where the scale is perpendicular to the ground. The forces on the scale were recorded for different RPMs. This can be shown in action here. The RPM is shown in the top right. The static thrust produced for each RPM was recorded on a table here. This was then plotted on a graph of static thrust versus RPM, which shows a linear trend in static thrust as RPM increases. This was expected. However, note that the thrust in flight is not the same as the static thrust due to propeller flex and due to the propulsion system being constant power, meaning as the velocity increases, the thrust will decrease. The next step is to make sure that the controls used do what is expected to on the albatross. To achieve this, the input mixing matrix has to be configured such that the following flight controls work as expected, shown in this figure here. The input matrix that was found to be correct is shown in this figure here. The longitudinal dynamic response to controls is shown here. This verifies that the sign of the change in trim angle of attack is consistent with the sign of the elevator input. This can be shown in the graph when the elevator goes down and when the elevator goes up. The angle of attack when elevator angle was changed was plotted for 3 mean aerodynamic chords. For each mean aerodynamic chord, 3 velocities were used. The velocities are 10 meters per second, which is the stall speed, 19 meters per second, and the maximum speed 27.7 meters per second. A general trend that can be seen at each mean aerodynamic chord is that the damping effect gets stronger as the velocity increases. This can be seen for 0% mean aerodynamic chord, 25%, and 50%. As well as this, as mean aerodynamic chord increases, so does the minimum angle of attack for the given velocity. This is shown here for 0 mean aerodynamic chord, here for 25, and here for 50. At 35% mean aerodynamic chord and at the cruise velocity of 18.9 meters per second, the graph of angle of attack versus time when the elevator angle is changed can be plotted. This is shown here. Using this plot, the short period frequency can also be obtained. This is obtained by experimental results as 21 radians per second. However, the short period frequency should be around 13.4 radians per second, which is quite far away from the experimental value. This means for a given mean aerodynamic chord, as velocity increases, the response will get faster and faster. However, you don't want it to be too responsive, meaning that 25% mean aerodynamic chord is the most appropriate for this scenario. The roll rate versus time for three different velocities can be plotted on graphs. This is shown in these three graphs for velocities 10 meters per second, 19 meters per second, and 27.7 meters per second. Clearly from the graphs, as the velocity increases, the roll rate also increases as the gradient gets steeper. As well as this, the gradient is constant throughout the entire time period when the input is active. It's clear that the damping in the yaw direction is much less than the damping in the pitch direction. This is easy to observe as it takes much longer time to achieve the steady state solution in comparison to this graph showing the time it takes to achieve the steady state solution in the pitch direction. This shows the change in angle of attack when the CG position changes in the y-axis. This creates a moment around the center of gravity as the thrust line does not go through the center of gravity. The moment induces an angle of attack on the albatross, however there is a y position of the CG where there is no change in angle of attack. This is shown to be around minus 0.03 meters in the y direction at the velocity of 18.9 meters per second and when the z coordinate of the albatross center of gravity is at 35% mean aerodynamic chord. This graph shows a lift coefficient versus angle of attack at different flap settings. One at 0 degrees, one at 20, and one at 40. The max lift coefficient for each of these are 0.9788, 1.1057, 1 and 1.2208 respectively. All of these max lift coefficients happen around the angle of attack of 15 degrees. As expected, the larger the flap setting, the larger the max lift coefficient of the albatross. This is the graph of the lift coefficient versus the drag coefficient for different flap settings. This graph shows the lift to drag ratio as a function of lift coefficient for different flap settings. At the 0 flap setting, the maximum lift to drag ratio is 14.25. This is achieved at the lift coefficient of 0.467. However, the CL max assumption was 1.4 and the maximum lift to drag ratio was 30. These are both far off from the experimental results obtained. This is a graph of CM versus CL for varying elevator angles. When the CM is 0, this is when the albatross trims. This is for a given CG position as the elevator angle varies from minus 15 to 15 degrees. The moment coefficient against the lift coefficients for different CG positions were plotted on a graph. The rate change of moment coefficient with the lift coefficient should be negative, which is shown at all the CGs plotted, which are minus 0.08, minus 0.1, minus 0.12, and minus 0.09. This is because it means it gives a large nose-down pitching moment, which is needed for good stability. This graph of CM versus CL is useful to find the neutral point of the albatross. The neutral point is the point where the coefficient of moment does not change with the coefficient of lift. This means that the line of CM versus CL will be flat. This means that the position of the neutral point will be close to one of these CG values as they have the gradient of nearly 0. As shown here, cruise flight can be achieved at 23 meters per second and at a throttle of 17 rpm.